today for this department in Uberlândia, where I have so many friends and colleagues and a long list of collaborations. So good afternoon, everyone. And I will talk about this this topic, and basically I want to explain to you today how we can squeeze light, okay, to the nanometer scale. And I will start with, well, UFMG. Everybody, or most of you, already heard about the university. We are here at the physics department. So those who don't know the campus, this is our central place, and this is the Hard Science Institute, and this is the physics department. Okay, so I belong to the Nanospectroscopy Lab. I share the lab with these two guys here, Ado and Leandro Malá. And I will give a very brief introduction about Raman scattering. Basically, Raman scattering is, this picture says a lot. It's the inelastic scattering of light. Okay, so we have this, here we have incident light with some wavelength. And for example, a molecule or something like a material, any material, you have the vibrational modes, okay, of the material. And when this material absorbs light, okay, the polarizability of the material can be changed in the process, okay, and the changing of the polarizability of the material generate different scattering components, okay, and one of these scattering components has wavelength which is smaller than shorter than the wavelength of the incident light. This we call anti-Stokes component, and another component has a wavelength which is longer. Okay, talking about photons, we can imagine here that in this case the photon deliver energy to the medium. Okay, this is why the light go to the redshift. And for the anti-Stokes, the light takes energy from the medium, okay, and this is why it's blue shift. The spectrum looks like this. We have the main component is the Rayleigh scattering, like just in elastic scattering, and this is very strong when you measure. So you have to avoid this huge guy here, which is just the elastic component of the scattering. And then we have the Stokes Raman lines, and we have the anti-Stokes Raman lines. This picture here just shows something like a semi-classical picture where you have the incident light. This, like what we have in this chart here, is like electronic states, and you have some vibrational energy states here. And what you have here is the electron hole pair being generated by the incident photon. And for the elastic scattering, they just recombine and emit another photon with the same frequency or same energy. For the Raman, the scattered photon has less energy, okay, compared to the incident photon, because a vibrational state is generated in the medium. For the anti-Stokes is the other way around. You start from an excited state, okay, vibrational state, and you annihilate this state in the medium. So the scattered photon has more energy than the incident photon. Classically, what you have is that your system is not static, okay? Your system can vibrate, and the polarizability. So when you shine light and the system interact with the light, okay, this vibration change, okay, with the system change with time because of the vibration, and you have this change in the polarizability And this is what caused the extra components of the scattered light. All right, so he is the guy who discovered this effect. His name is Raman. He discovered this effect in 1928. This is the instrument that Raman used. It's a spectrograph. Okay, the light comes from here. You have a dispersion of the light. Okay, and then what he did, he just placed. Okay, so you have some liquid here, some organic liquid. You have the sunlight coming. He placed a filter to take only the violet component of the sunlight. He illuminated a liquid, and he had the scattered light, and he filtered the scattered light. Okay, and he saw that he has some components that were with different color or different frequency of the incident light. He called this the negative absorption of radiation. It's a very interesting name. And he received the Nobel Prize in 1930 for this discovery. The point is, so this is, I like to show this picture here because this was another very important guy in the Raman scattering, the history of the Raman scattering, Sergio Porto. He unfortunately died very young in 1979, but he worked in the Bell Labs, United States, and he developed, he introduced the laser in the optical spectroscopy, and he developed a lot of instrumentation, okay, to make modern the spectrometers that we see today. The model, okay, was very much planned by this guy here, the Sergio Porto, and he used the laser for the first time to make Raman scattering, and of course the efficiency of the process was much better, and he developed a lot, and not only for the instrumentation but also for the theoretical part. Okay, you have the Porto notation, where you have a very efficient way to make some analysis about the polarization of the scattered light. And then this is a very important researcher in this area. Okay, so why we give so much attention to this effect, and why we have to go beyond the instrumentation that was developed by Sergio Porto and others. First, so Raman spectroscopy is a very nice probe, okay, to study the structure of crystalline solids or molecules. So the chemical community, the chemistry community, they use Raman scattering a lot to study like which kind of molecule you have, even to study different types of chemical processes, because every component of the scattered light carries a lot of information about the material. Okay, and it's a very versatile technique. It's clean. Okay, photons are very clean. They travel alone. Okay, so you just send a photon and collect the photon. So the photon it's easy to deal with photons. Okay, and the amount of information that you get from Raman spectroscopy is a lot. It's one of the main techniques for studying solid state physics, solid state systems. But there is a very strong limitation for studying Raman or any other optical technique, which is draw here. This chart here was taken from this paper here. This is a very nice paper from the Nobel Prize, the Stefan Hell. And this is this limit here, the half a wavelength of light. Okay, so the visible light, we have something around 500 nanometers is the wavelength of the green light. Okay, so half wavelength is something around 200 250 nanometers, and the optical microscopy works very well up to here. Okay, less than 200 nanometers, everything becomes blurred. So you cannot make a very nice optical microscope. Okay, the best optical microscope to see things which are smaller than half of the wavelength of light. This is a very fundamental thing. It's related to diffraction, and I will explain to you the reason of this limitation. But the fact is that everything that goes smaller than this scale, which is given by the wavelength of light, become very blurred in any optical microscope system. And of course, the nanotechnology, for nanotechnology, this is a very strong limitation. When I was a PhD student, my dream was to have a well-resolved Raman measurement. So this is because I did all my formation on optical spectroscopy of nano-objects, and you just get information from a very large area, but the object is so tiny, then everything is confused. And I will give you the most clear explanation that I can give about this limitation. So this is the memorial for Ernest Abbe. This is in Jena. And this guy just established a limitation, something that is called like the Abbe limitation. Okay, you cannot resolve 2-point sources which are closer than mainly half of the wavelength of light. Okay, here we have the 0.621 lambda. Lambda is the wavelength of light, and this is the n is the refractive index of the medium, and the sin alpha is the aperture angle of your objective system. Okay, then if you have some, I will explain this better, but this is what we call the numerical aperture. If you have a very large numerical aperture, your system, your resolution improves. Well, this is difficult to understand if you know geometrical optics. Okay, like for example, optical microscope. If you take, for example, here is the object. Okay, a very tiny object, and then we know we have two objective lenses. Actually, we have one objective lens at least. And then we have all this optical geometrical path. Okay, you have the light in the focus, and then here we have the real image of this object, and then this real image is between the eyepiece, okay, and the focal point of the eyepiece. So we have now a virtual image of this primary image, okay. Then we have a secondary image, which is what we see. And the secondary image is very large compared to the object. Then we see the object large. Okay. Well, this magic here is possible because we are dealing with all these nice straight lines. Okay, which we teach. We say, okay, so the light beam comes here and do this and do that with our rules. And say, okay, this is very simple. But the point is that this object here, this is possible. This picture is possible because this object here is much larger than the wavelength of light. Then the light goes straight, like straight beams. But the fact is, when you go down to the size of the wavelength of light, you start to have a lot of diffraction. So here's a very simple picture. We have a wave, okay, a plane wave comes to some slit here, and the size of the slit is the same size of is comparable to the wavelength of the wave. Then we see that we have a lot of diffraction. Okay, but the same is not. You cannot see the same if the size of the slit is much larger than the wavelength of the wave. So it looks like the wave just goes straight. Most of the wave just goes straight. Then here's the case where the optical microscope works well. If the objects involved are much larger than the wavelength that we are dealing with, it's okay. But if the object is small, at the same scale as the wavelength of the wave, then we start to have problem here. And it's not just a matter of diffraction, okay? It's not just a matter of the way that the wave spreads. You have a very serious problem here, because when you have this kind of obstacle, some part of the wave just stay there. This is what we call the near field. You have the far field, where the wave just go and propagate, but we have some energy that stays stuck here, which is the near field component of the wave, okay? And now I will explain. Well, then we try to do with when the human being understood that the problem was the comparison between the size of the object and the wavelength of light, the first thing that was tried, successfully tried, was to decrease the wavelength of the source, okay? Then instead of using light, we start to use electrons. Then we know that the wavelength of the electrons can be tuned, okay, by the kinetic energy of the electrons. Then you just make this electron accelerator, which is, for example, this Titan microscope. This is like a electron accelerator. So you just make a lot of momentum you just give a lot of momentum for the electrons, and the wavelength of these electrons is very small. Then you can make images, not with like light waves, but with electron waves, okay? You have very nice images. So this is an electron microscope, okay? It's a microscope which use electron waves, not light waves. So the wavelengths of the electrons waves is very tiny. Then you don't have the problem of diffraction. Then you can see like a carbon nanotube very nicely here, for example. Another approach is to use the scanning probe method. You just goes with a very sharp tip, okay? And you make a feedback process. And if you go scanning your surface, okay, and you feel how your surface, the topography or the forces involved there, okay, and then you can make this type of touching the surface with a very sharp tip, okay, and you figure out the shape of the objects there. This is like most like for chemical forces, that the interaction between the tip and the surface. Then you monitor these chemical forces, most van der Waals. But we also have the scanning tunneling microscope, where we use the electron tunneling, okay? And we know that if you approach the tip from the surface, okay, you can control the tunneling current by this distance, and you can use the tunneling current as a feedback system for understanding your surface. Well, these two techniques work very well. You can have a lot of information from STM or AFM This is atomic force microscopy. This is scanning tunneling microscopy. You can see atoms with both of them. Okay, this is a carbon nanotube. This is a silicon surface. Atoms in a silicon surface. This area grew a lot in the last decades for the nanotechnology, but we still want to do light. Okay, we still want to do optical spectroscopy. So this is a way to see the objects. This is a way to study a lot of things for these objects, but we still have the problem. We want to use light because this is very useful. So I will give you a glance about this, the problem of diffraction, the source of the lack of limit, spatial limit. Okay. So this is what we call the angular spectrum representation of the optical fields. If we have like a point source here, something or a very tiny source in a plane, this the z direction here is the direction of propagation. Is actually the direction that I want to analyze the fields which are emitted by this source plane. Okay, and the angular spectrum representation. What we do is we describe the field, the electrical field, as a plane z, okay, some coordinate z, as the sum, the integral sum of the Fourier components of the field, okay. We just describe this as a sum of plane waves, and we sum over all the spectrum of spatial frequencies. Okay, but then what we can do here, we just solve the Helmholtz equation, which is this equation here. It's basically the wave equation in free space. Okay, and the solution of this Helmholtz equation along the z direction, you find that this Fourier components of the field at the position z can be described by the Fourier components at the plane source, okay, times a propagator. Very simple. So we have all the Fourier components here, okay, and then you have this propagation here along the z, okay, direction, and then you can have the Fourier components at the plane z. This is because it is a free space propagation. Well, then if we put this solution here, because okay, so you know the source. Let's suppose you know the source, okay, you understand the source, or of course we want to measure the field at z and understand what the source is. This is what we do. I measure here, and I want to reconstruct my source. Okay, I want to understand what's the source. So I want to understand these guys. And here I have a very simple exponential function. Okay, but the problem is this kz guy here. The wave vector of light, the component of the wave vector of light along the direction of propagation. So the wave vector of light is just lambda over 2 pi. Okay. This is the norm of this k. Okay. So what's k? K is a number. The modulus of the vector is a number. It's given by lambda over 2 pi. Okay. Now, but this is a vector, so it has 3 components. So the modulus of k is a real number, but the components, they can be complex. So you can have imaginary part. Okay, this is a complex number. So you can have imaginary parts of the spectrum. So some of the components can be imaginary. And so if we decompose kz as a function of kx and ky, okay, we just take the k square minus kx square plus ky square, and we write this in this way. We just see that we have two possible situations, okay? Because the k square is absolutely 2 pi over lambda, and the k square is absolutely the square sum of these guys here, but some of them can be imaginary, because if we take this and now we subtract, okay, let's see along kz, okay, if we subtract 2 pi over lambda square by these two guys here, we can have two possible situations, okay? If they are smaller than k square, if this sum is smaller than k square, okay, kz is a real number, okay, because this square root here is positive, so this guy here is positive, and kz is a real number. If kz is a real number, okay, because this will just be a imaginary exponential, so this is a wave plane, plane wave, okay, propagating plane wave. But if this number here is larger than k square, then kz is imaginary. Then we have here a very strange situation, because we don't have the e to iz, okay, as a plane wave, but we have I times I, we have e to minus z and blah, blah, blah. So this is an exponential decay function. So this function just decay if you take this along the positive z, okay? This function here just decay as it goes far from the source. So it means that all these components here, if you take all the spectrum which is out, okay, if you take the kx and kz, kx and ky spectrum of possibilities here, everybody which is out of this circle here, all the spatial components, they just don't propagate. They go evanescent from the source, okay, and they decay. So the field decays very quickly, actually. In the practical, so like something like after 10 nanometers, okay, the field just goes away. So this path here just goes away. So there's a problem, because as I said, we want to reconstruct our source. We want to measure this, and then we can try to reconstruct our source. But there's a lot of information which is lost. Actually, the large wave vectors at the, okay, so the spatial frequencies, the large spatial frequencies in the plane perpendicular to the direction of propagation, they are lost. They stay in the near field, okay? We call this the near field. And then we get only the far field, which is the short spatial frequencies. So this is like if you heard something, okay, and you filter the components of some components. For example, if you listen a voice, okay, and some components, like let's suppose the high frequency components are lost, okay, you cannot hear that thing very well. This happens, for example, if you have a party, okay, far from you, okay, the high frequencies, they don't, for different reasons, okay, the high frequencies don't get to you, and then you just hear the low frequencies, okay, then you just hear the boom, 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 boom. You cannot reconstruct the music or the sound very well, okay, because you don't have the information, okay. Most of the information of the high frequencies are lost. Here's something very similar. Because we lose a lot of information, the information stays at the source, we cannot reconstruct the source very well. So in other words, okay, we are lost. So all the information outside of the circle here is lost. It means the information stays at the plane source, okay? Then we have a delta K, and the size of this delta K is 2 pi over lambda. Well, if we take the Fourier transform of this delta K is delta R, so spatially, we are confined to something. Let's suppose this is a Gaussian distribution, just to make an example here. Let's suppose we have a Gaussian distribution here. So if this Gaussian has a limitation of 2 pi over lambda, in the real space, we have the limitation of lambda over 2 pi. It means like the maximum K that we can have is 2 pi over lambda. So the minimum space that we can have is lambda over 2 pi. So you cannot squeeze light, okay, more than lambda over 2 pi. This is for a perfect theoretical analysis here. So this is just Helmholtz equation, Fourier transfer, Gaussian distributions, but the real world is worse because you cannot even get all the components that propagate. So you cannot have a perfect microscope. Then we have the numerical aperture, which means you can go very close to your sample and you increase the numerical aperture a lot. I mean, you increase this angle here a lot by decreasing the work distance. So you improve this number here, but even you cannot go for NA, even if you use like immersion oil objectives to improve the match of refractive index. So you increase the refractive index putting oil in your sample, okay? But even in this case, you cannot get an NA larger than 1.45, something that is a kind of limitation. For very, very small working distance objectives, something like 100 micron working distance, okay? So this is a very strong limitation, and the reason I think is clear now for everybody. But there is a way, okay? So what we have to do? So I apologize. This is in Portuguese, but I will read here. So let's take a break here and think. What's the problem? Organize the ideas. So if you don't understand the math, you understand the idea. You have some components of the light that if you have a source, a light source, some components of the light do not propagate. Okay, these are called the near field components. They just stay at the source. Okay, this is an evanescent field. Okay, it goes down very quickly when you go far from the source. So these components, if you don't get these components, okay, if you don't detect these components, you cannot reconstruct your source because you don't have all the information. Okay, it's like when what's called telefone sem fio, wireless, that we whisper something, okay, to the person near you, and this information is going badly, and the person on the other side of the room just don't understand the information because everything is lost in the way. So this is the same problem. Then, for example, if you want to make a Raman of a carbon nanotube, okay, everything is blurred because this is an optical microscope. So this is a Raman mapping, okay. Every spot here is a Raman. Is the intensity of a Raman band, okay? But we see how the image compared to AFM is so bad because we cannot squeeze the light enough, okay, to get this image here. So what can we do? We have to go close to the source and somehow fish these near field components. This is the trick, okay? Then we have to make some channel and like a bandpass. So this high frequency, these spatial high frequency components, they just become propagating. Okay, so you have to go there and say, okay, come to the detector. Okay, so this is the concept of an optical antenna. Actually, the optical antenna, if you take the one of the concept, okay, so plasmonic guys, they say very strongly that this is the concept, but this is one of the concept. The optical antenna is something that make the propagating information to become like a localized information. Okay. In other words, it is a channel between the near field and the far field, and vice versa. Okay. It's like any antenna works like this. You get a wave, so you translate that wave in something, okay, which has the same frequency of the wave, and then you can work with that information. All right. So this is basically what we do. We go with an optical antenna very close to the source, okay, and then that information is transferred to the antenna, and then the antenna just make that information goes away. Okay, so the information is there, very close to the sample, and then that information which is stuck here, the antenna just take the information and send to the far field. This is the trick. This is what we do, actually. We take a metallic tip and we approach to the source. And this is not like AFM anymore. This is a Raman map. And the resolution here is about like 10 nanometers. And what we do, we just make some scanning probe. But now our tip, okay, is an optical antenna. And it takes these components of light and send to the far field. All right. So the limitation today of this technique, this is like a single molecule. It's just one molecule, okay? This is a Raman scattering of one molecule. This is the normal mode of vibration of a single molecule. And here, these guys, they make like Raman mapping at sub-nanometer scale. It's actually very difficult to understand how they can do this. So theoretically, this is really weird, okay? But it can be done for like a angstrom, at the angstrom scale, okay? This is making like ultra high vacuum STM system. But the early idea was this guy, the Sinji, he has this idea to put like this like a biological sample, and he has this idea to place a plasmonic structure, very tiny plasmonic structure, okay? And this is like a historical fact that this guy, he sent a letter to Einstein in 1928. And he said, look, Einstein, I had this idea, so you are very smart. I want to know if this makes sense. And his idea was exactly to place an optical antenna here, and probably he could see small things smaller than the wavelength of light. And it's funny because Einstein understood the idea, and the answer, there's the letter with the answer. And the Einstein like say, okay, this is a very nice idea. I just think it's useless. But the idea is very nice. So, but anyway, this Sinji is the first record that we have. Okay, of course, some Russian probably before had the same idea, but we don't have this the history as we know. Sinji was the first guy to think about this. So this was like, this is near field optics. Okay, you can do luminescence. Most near field optics is from luminescence. You can do terahertz, but TESS is difficult because the Raman intensity is very small. So Raman is really a nightmare. We have these modern spectrometers. We have a lot of power, lasers, very nice CCD system for detection. So nice, now we are spoiled. But Raman the Raman signal is very weak. Okay, so the first test took a long way to be developed, and was Renato Zenobi, this Swiss group. In 2000, they give like a comprovation of the first test. The first test in the south hemisphere of Earth was made here, and was made by the person from Uberlandia, which was Newton. Actually, Newton did this experiment. Okay, this was like Newton's experiment. At that time, Newton was here at the Nanospectroscopy Lab doing a postdoc, and now he went, well, not now, but he's back to Belém. But that time he was in a sabbatical from Uberlandia here, visiting the lab, and he did this experiment here. And this is the first test of the south part of the Earth. Well, I will, and I don't have much time, but I want to explain how these antennas work. One way is just the lightning rod effect. Okay, you just like if you make like the light. Okay, if you illuminate a metal, okay, with some frequency, you make a motion. You drive the electrons, okay, at the metal. And for example, here, if the polarization is parallel to the tip shaft here, okay, you just make a motion of electrons, okay, very close to the tip. And of course, when these electrons go close to the tip, you have a lot of energy there, okay? Then this is like the lightning rod effect. This is why we have very strong electric fields at the tip of a sharp metal thing, okay? Then we use this, and we have to use the polarization parallel to the tip, okay? We cannot polarize. Well, we have the same effect, but it's not as strong. This is like the surface charge, okay? Then we generate like a dipole, oscillating dipole, and this tip will emit light at the same frequency. And this is how it works. Well, so making the tips is something not trivial. So in 2012, so we used to do this like a chemical etching. We also have a very good collaboration here from Haigner, who work here with us a lot, helping us to understand all these chemical processes to make these sharp tips here. Also, a very important contribution from Uberlandia to this story here. But these guys, they make some template stripe pyramids, and they fill this with gold, and they come with the glue and fish the gold and make these pyramids, and they were very good, okay, to make this. Much better than the chemical etching tips. But we have the plasmonics. So these tips, they don't use the plasmonics because we have this localized surface plasmon resonance, which is basically, well, these like very small nanoparticles, metallic nanoparticles. You have the resonance, and the frequency of the resonance depends on the size of the nanoparticle. Basically, it's a half lambda antenna. I will show here. If you get a metal, okay, which has the size of the wavelength or half size of the wavelength, what will you do? And let's suppose you shine light in a metal like this, and the size of this thing, okay, is half of the wavelength. Then you nicely polarize this metal, okay, and then you generate this local surface plasmon resonance. This is why you cannot put a metal inside of a microwave, because the microwaves, they have something, the wavelength is comparable to a microscope object. So you make surface plasma resonance in like a macroscopic objects inside of a microwave furnace. But here we are dealing with nano objects. Okay, it's not exactly a half lambda antenna because the metal is not perfect, but it's something that we can tune. And when you do that, the response of the optical antenna goes much higher. Okay. This was the PhD thesis of Thiago. Thiago is a former student here and is also work at Inmetro. And what Thiago did, he just used a focused ion beam to make a stripe in these gold tips, okay? And the idea was to make like a half lambda antenna, just make this stripe here. We just take and try to induce plasma modes here, the localized surface plasma, okay? Of course, you have to match this with the wavelength of the light, and then use microscope. I don't have the time to explain this, but he used a transmission electron microscope to see the lobes of the surface plasma modes. Okay, then we come with this idea here, which Thiago nicely developed, which is this what we call the PPT, the plasmon tuning plasmon PTTP, plasmon tuning. Well, what's the other T? Well, pyramid. So the idea was to take the pyramid of those guys, and we stop the process here and make another tiny pyramid. And this small pyramid here now is tuned to the wavelength of light, okay, which we want to use. So also Thiago also studied this with the electron microscope. He was able to do the tuning, like studying the size of the pyramids, okay, which match the wavelength of the light. And he tested the pyramid, and we saw a lot of enhancement of the Raman signal. Like if you approach, so this is the Raman signal without the pyramid, and he approached the pyramid, and he got like a lot of light. So a lot of enhancement, okay? And this is very important for tests. We need enhancement. So this is the image of a carbon nanotube, okay, using this pyramid. And this is just a graphic showing how the signal goes up when you approach the pyramid, okay? So this was the FIB tips. So the signals goes up. This was like the template stripped pyramids, but this was the PTTP. Okay, and the enhancement was much higher, and this was like a game changing actually. So this technology is patented in like US, Brazil, China, Japan, European Union, and now this is very nice. You see how we use this is like a Inmetro logo made with defects, okay, in a graphene sheet, okay, and this is what we get. This is a Raman map of this Inmetro logo without the tip, and then we can resolve very nicely using this system. I will just give you a glance about the Moore patterns. When you rotate two graphene sheets, you can have these Moore patterns. This is a very fancy conductivity at the small angles. And this is a kind of reconstruction when you have this Moore very small angles, okay? the Moore pattern, they become something weird. Like you can have like the graphene system here, but we can have these lines of what we call like morphological defects. That is at very small angles, okay, became like with this shape here, and people can see this with electron transmission microscope. And well, I'll not give much details, but the main result that we have with this technique so far was to measure twisted bilayer graphene, a Moore pattern of a twisted bilayer graphene with theirs. Okay, so this was almost, because this is the limit of we can have up today of seeing a network of atoms, okay, a crystal lattice with light, because this is a crystal lattice with light, visible light, okay. And this was like a twisted graphene, and this is a test. Basically, this is the width, okay. The mapping here is the width of a Raman band, okay, and basically the Raman band become like broader at these defects. I will not have because I gave much more focus to the technique itself. But this was a very important result, because really this was like why this is so important is because it's the first image of a crystal lattice made by visible light. This is the breakthrough, and this is why this result was so important, was published in Nature. I will go not much in details here, but we still studying like nano-objects with these techniques. We can see how, so this is like a small graphene flakes. This is how they look if we make Raman mapping, just common Raman mapping. If you use a VTEX system or Horiba system, this is what you see. But we can use tests to study these graphene systems in a lot of details, okay? So we develop here like a mass production of graphene. We study like small flakes. We take like 100 data from these flakes. I will just because I want more. Okay. Then in this, you are interested how these fields they work. Okay, we measure the shape of the field using these tiny graphene flakes. Okay, we understood what's the shape of the near field. So if you are interested to understand how the sample, how these tips illuminate the sample, okay, and how the sample illuminate the tip, take a look at this work here. It has a very basic and clear story, and we can now reconstruct test images much better, because now we understand the shape of the field. Yeah, I'm sorry, I'm jumping here, but I really want to show this. So the technical aspects of this development. So this was like homemade things. So some parts here. So Newton helped a lot, actually. Some parts like we have here scan head that we use. We made this by hands. Okay, all the electronics was developed. All the plasmonics part, the development of the tips. The instrument is very confusing, like a lot of parts. And this was all homemade. It doesn't look pretty, okay, as we see here, but this was developed by these three, a lot of people developed here, but these three guys here, they are former students, Thiago, I mentioned, Cassiano, and Hudson. They create the startup, LabNS, okay, and we had like a project to make this instrument here, this monster here, a commercial instrument. And now this is a reality. Okay, so the instrument becomes something like this, very fancy. They developed all the electronics. They improved the electronics a lot. They have a controller that they do by themselves. All the mechanics, the optical mechanics parts, the tip, okay, the plasmonic tips. So everything, the software is very nice. If you want to, this is applicable for other types of systems too. So this now is well, I'm not making advertisement of my company. I don't own this company. Okay, this company is not mine. We just transferred all the technology for them. But if you want to have this technology in your lab, you should talk with these guys. This is an advertisement that I do because this is a hard tech company and it's not easy to develop this in Brazil. But there's they already sold out one of these instruments to Germany, and well, is a good story because it's an inversion of the natural flow of technology. So I stop here. I thank you again for your attention and for the invitation.
Thank you very much, Luiz Gustavo, for this very didactic, interesting talk. We are open to questions now. Does anyone have a question? I have one. Did you guys do any study of what are the best metals to make the tips, the pyramid tips, or any theory study, or it was just trial and error?
Okay, so as I understand the question, this is a very good question. Okay, so Cassiano just remind me, plasmon-tunable tip.
Yeah.
Okay, so this is a very good question because we do gold tips. Gold is a good metal for many reasons, but it's not the best metal. Okay, the main reason for gold is well, you can have the localized surface plasmon in the visible range, but it's like borderline, like in the red. So red is not very good for Raman. Good for Raman is for the blue. So it's not very efficient, but we use gold for the chemical stability, basically.
Okay.
So if you make something by gold, you can just leave it, and the gold just stay forever because it's very inert. Okay, silver is a nightmare. If you made something by silver, so in a few days the silver becomes like black. It's because you have the oxide. So silver is very unstable, but silver is much better than gold for many reasons. So the surface, the resonance goes to the blue part, okay, green and blue. So they are much more efficient. But we have this problem of the chemical instability.
Okay.
But now one line that we are dealing is mixing the metals, try to tune in the resonance, okay? And this is ongoing study, okay? So this is in the science field, stay in the science field, but this is something that it's under development.
Okay, thank you. Djalmir wrote something here on the, can you see what?
O Djalmir, é o seguinte, então, ok. look, when the object absorbs light, okay, some part of the light becomes heat. So this is something you generate a lot of excitations in your system, okay, and there are a lot of channels of decaying channels. We call these decaying channels. Okay, so you shine light to your object, and the electrons absorb the light, so you generate a lot of electron hole pairs. Okay, this is for a molecule or for a solid or anything, and then the electron will decay back. Okay, that energy will not stay like with the electron forever. Okay, then you have the decaying channels. One very important decay channel is the light that goes away. Okay, so if you don't have if you don't have resonance, or if the band gap is too large, for example, if you shine light to the glass, the light just goes away because the energy gap is so large. So the electron hole pairs, the light is not absorbed. But for example, if you shine light to a black object, so the light is absorbed. And then what's the decay channel? Okay, it becomes heat. Mainly. So a black object, you don't want to use a black t-shirt under the sun, because that light will become heat. Okay, this is a decay channel for that object. Okay, so this is different from what we are talking here. Any object, this is not light absorption. So the evanescent part is not light absorption. Okay, it happens whenever you change the refractive index. Okay, let's say that like this. Whenever the wave see any change in the medium, okay, you have this evanescent part and the propagating part. So of course the energy is stuck there, okay, but that thing is not being absorbed. Is not like that. It is absorbed. So you have a high local energy, okay. And also you can have these local surface plasmon resonances, and this can become a channel for energy transferring, okay. But this is different from the light that is absorbed and becomes heat. So it could be a channel to make this process, okay, more efficient. Like you have an object that we have the resonance, but this is not the concept is different, okay. So it happens in any system. It could be biosystem or solid or anything. And of course, if you come with a tip like this, okay, and the tip has a high density energy, okay, and you approach the tip to a bio thing, the energy is high there. So that energy can be locally transferred, okay. But this is different. But I think, I don't know if I made it clear. This is different from like a light being locally absorbed by the tip. So the near field components, this is not light absorption, okay? Not sure I made it very clear.
Djamir, I think, doesn't have a microphone, but he can answer. Yeah, he doesn't have a microphone.
Can I give an example?
Yeah, sure.
So, for example, people use this to local heating. This is a fact. For example, there's some treatment. So you inject nanoplasmonic structures to some place. So you want to kill some kind of cell, for example, a cancer cell. So people inject some type of tiny metals, tiny cylinders or something, and you shine light in the wavelength of the local surface plasmon resonance, and they locally kill the cells there. Okay, so you make a very special chemical compound around the tiny object that attach to the cells that you want to kill, and then you shine the light, and they make the local surface plasma resonance, which is the near field component, and that local energy can kill that specific cell. Okay, this is a very successful way to apply plasmonics. There's a famous researcher in I'll not remember now, but this is a growing area. Okay, killing specific cells with tiny plasmonic metal structures, shining light in the resonance frequency to locally hit that thing.
Okay. So Djamir doesn't have a microphone. He's thanking you. So I assume that the answer was he understood the answer. I have another answer. I have another question. You showed some very nice results for the twisted bilayer graphene. I am wondering, I was at the March meeting these past 2 weeks, and I saw some very nice STM results showing charge order in the twisted bilayer graphene. Would Raman be able to observe charge order in bilayer graphene? Because you mentioned that was the first crystal optical measurement image that was made. I assume that's because the lattice parameter is very big, right? For the twisted bilayer, well, for some angles of the twisted bilayer graphene. Yes. Do you believe you could observe charge order?
Well, I don't know. I mean, these things are somehow connected, but well, okay. So STM is very sensitive to local density of states. Okay.
Yeah.
Raman is more related to electron phonon coupling.
Okay.
Everything that involves electrons will contribute somehow to the Raman, but not in a clean way as the STM see the local surface, the local charge density, and in the clean way that Raman see the electron phonon coupling. So what we see here is that the electron phonon coupling, it's much stronger, okay, at some parts of the twisted bilayer, okay, and we speculate that all that physics, okay, involved in the transport of these structures is related to the electron phonon coupling. So this is what it's really seen here, okay. But of course, if you have high local charge, localized anything that's electron localized, okay, will be involved in this Raman process, but it's not the primary fingerprint. So it's difficult to say, but you're right. To be honest, okay, to be clear also, of course, we didn't see atomic lattice. We took the advantage that at very small angles, the lattice parameter is very large, so it becomes like 10 nanometers or something, then we could see. Okay.
Yeah. Well, but these systems are very, very hot right now, right? Yeah. They are being studied. I could notice that in the March meeting there were tens of talks about twisted bilayer graphene. So I took note of the paper here. I'm gonna take a look at it. Any more questions? Anyone in the room? Gerson? Do you have any questions?
Can you just make a comment to test the mic? Can you hear me?
Sure. Yeah.
Hear it well? I'm going away from the computer. Can you still hear me?
Yep. Well, it's kind of noisy, but I can understand what you are saying.
So it's better if I stay here, I guess.
It's better if you stay there. Yeah.
Okay, so my question was actually the same as Georgie about the material, and I think I actually asked you this question a couple of years ago already. So the ideal material for the tip is something with strong density of states and plasmonic response, right? So there's probably a lot of research on better materials and so on. Of course, the chemical stability, as you said, is really important. And just as a suggestion for people here working with topological insulators, you have these higher order topological insulators. The main property is a large density of states at the tip. And so this could be quite interesting. There's the chemical stability and the plasmonic response that needs to be studied, but it's an intriguing material that could improve this resolution, I guess. I don't know. Just
yeah, no, you're right.
Vague comments.
Anything that has a lot of electrons, and you can make like localize something, okay, some response, some because the local surface plasmon resonance is one way to go. Okay, if you figure out any way to confine, okay, light in a material system, okay, and tune any type of resonance, this should work. This is one way we use it. But I agree with you that should not be the only one. And topological insulators, if you see the possibility, sure, should work. If you have any ideas, please contact.
Yeah. I don't know many works about plasmonic response on topological insulators, but it would be nice to start reading about it and see if we have some ideas around here as well. Let's see.
Yeah.
Thank you.
Gerson is the person of the good questions.
We are used to him asking very good and very tough questions.
Yes, every time Gerson takes the microphone, I say, "Oh, here comes Gerson again."
No. Yeah, there comes trouble. There comes trouble. Any more questions? Anyone? I see that Tomé is here, so maybe he has some thoughts about materials. Hiroki left. So I believe not. So if there are no questions, let's thank the speaker again. Thank you very much, Luiz. It was a very nice talk. I will. I forgot to ask you in the beginning if I could record the. It's a little bit too late to ask now, but I forgot to ask in the beginning if you agreed to be recorded, because we will put the video in our YouTube channel and advertise the video. A lot of people, some people wrote me today saying that they would not be able to attend the seminar, but they asked me if it was going to be recorded, so it's going to be available in our YouTube channel. So if you want to advertise the video to collaborators, etc., I can send you the link later. We should have it posted next week. And I will be writing you an email to ask for these slides. We put these slides together with the video so people can have the slides too.
Okay, sure.
Okay, so thank you very much again.
Thank you very much. So thank you again for the opportunity to meet you guys. I should go to Uberlândia soon to visit. So I see many friends here in the list. So I want to say hello to all my friends in Uberlândia and acknowledge again for this nice invitation.
Okay, thank you so much, and we look forward to having you here in Uberlândia. Otherwise, we see each other in Ouro Preto in May.
Exactly.
Okay. Okay. Nice meeting you, and have a nice afternoon.
Thank you. Bye.
Bye. eu peço que os alunos do curso continuem na sala para a gente ter a primeira aula. Eu já vi aqui que os...
Jorge, você
Alô,
vai
Gerson?
interromper a gravação?
Então tá, pessoal.
Sim. Tchau, tchau.
Pessoal,
Tchau, tchau.
valeu, obrigado.
Obrigado.
Sim.